day, everyone. We at Hosokawa Micron Powder Systems welcome you and thank you for attending our fourth in the series of educational webinars entitled Particle Size Analysis, focusing on aerodynamic sieving. Let me point out, if you have a question during this presentation, you may submit your question online. Please refer to the question and answer pane on your screen. At the conclusion of the webinar, we will try to accommodate all of the questions during our question and answer forum. My name is Bill Brown. I am the Division Manager of the Chemicals and Minerals Group here at Hosokawa Micron Powder Systems. I will begin the presentation and then hand the presentation over to Mr. Timothy Calvo, a Product Manager for Laboratory and Analytical Equipment. Here is a brief introduction or table of contents for the upcoming seminar. We'll start off with a brief introduction of the Hosokawa Micron Group and Hosokawa Micron Powder Systems. Next, we will briefly discuss mathematical models used for particle size distribution analysis, followed by common methods and instruments. Since the focus of this webinar is on pneumatic sieving, we will have an extensive discussion and presentation by Mr. Calvo, discussing criteria for selection for pneumatic sieving, application fields, how it works, and features and benefits. And then we will follow up or wrap up with a summary and a question and answer forum. Hosokawa Micron Powder Systems is a division of the Hosokawa Micron Group with headquarters in Osaka, Japan. We're the global leader in powder processing equipment manufacturing, employing over 1,500 employees worldwide, with production facilities in 5 countries and 12 research facilities and state-of-the-art technical centers. Hosokawa Micron Powder Systems is the North American division of the Hosokawa Micron Group, supplying products and services in the chemicals, minerals, food, and pharmaceutical markets. Our brand names include Micro, Alpine, Micron, Vrikonauta, Majak, Stott, and Vitalair. Our division was founded in 1923 under the name Pulverizing Machinery. We are located in Summit, New Jersey, and have approximately 50 employees here, and have been part of the Hosokawa Micron Group for approximately 23 years. Before we review the models and common methods for particle size analysis, it is essential that we first define the term particle size distribution. Particle size distribution of a powder or granular material or particles dispersed in a fluid is a list of values or mathematical function that defines the relative amounts of particles present, sorted according to size. And the method we use to determine particle size distribution is called a particle size analyzer. There are 2 known mathematical models which define the relative amounts of particles in a sample. The first here of which is known as the log normal distribution. This is a single-tailed probability distribution of a random variable whose logarithm is normally distributed. In this case, the x-axis is the particle size, and y, of course, is a function of x. And as seen here on the left graph or left table, this is the cumulative distribution function, while on the right we see the probability density function. The other model is called the Rosen-Ramler distribution. This is introduced in 1933 and describes particle size distribution extensively and has been since been used most commonly in the industry for sieving. This function is used when generating particles via grinding, milling, crushing, or classification. The graph here on the left shows the cumulative function distribution, and the graph on the right shows a probability density function. And as you can see here, y is the cumulative passing fraction, d is the particle size in microns. D prime is the finest number, or the particle size at 63.2% passing, and n is the uniformity index or standard deviation. Before we review the models for particle size analysis, one must first ask himself, how do I select the right type of analyzer? Here are common criteria for selection. They include, what is the particle size range of the powder? What is the particle size range of my sample? What are the characteristics of the powder? For example, is it soluble in water or alcohol? Is it cohesive? Is it friable? How poorly or well does it flow? Does the powder flow? Also, what are the types and formats of information required from you or from your customers for analysis? For example, do you need only one or several data points, or or do you need a continuous particle size distribution? Are key determinants such as median, mean, D10 or D97 important? And do you need to know information, for example, standard deviation? While the primary focus of this presentation is aerodynamic sieving, we wish to first present a cursory review of the most common methods, including optical counting, sedimentation techniques, laser diffraction, electroresistance counting, acoustic spectroscopy, and sieve analysis. Optical counting is simply measuring particle size via scanning electron microscope or other types of microscopes, as seen here. For the sedimentation technique or sedimentation principle, you must have a fluid or liquid of known properties. The particles settle in this fluid, and you're measuring the gravity-induced settling velocity of the different particles. The rate that these particles fall or settle is defined by Stokes' law, as seen here. An example of sedimentation technique is the setograph, where we can measure particles from approximately 0.1 microns and upwards of 300 microns. The next method is electroresistance counting. In this case, a liquid carries a population of particles through an orifice. There are two electrodes and a voltage is applied across the aperture. The aperture is located in this tube that's immersed in this liquid here. As the liquid and particles pass through the orifice, there's a momentary change in impedance. The size or the volume a particle displaces is related to this impedance. Another method, not as common, is called acoustic spectroscopy. It simply employs ultrasound instead of light for collecting information on the particles that are dispersed in a particular fluid. The next, a very common method used, is laser diffraction. A laser beam, if you will, illuminates the passing particles in the scattering volume. These particles scatter light, generating very unique angular scattering patterns. These distinct patterns, or diffraction angles, are related to particle size, and thus a particle size distribution can be obtained for a given sample. Again, this is perhaps one of the most common methods used to date, and is applicable for particle size ranges from approximately 0.4 to 2,000 microns. At this point, I would like to turn the presentation over to Mr. Timothy Calvo, Laboratory and Analytical Equipment Manager here at Hosokawa Micron Powder Systems. Tim is our in-house specialist responsible for our aerodynamic sieving product line. Tim is a veteran in the industry, working for Hosokawa over 20 years.
Thank you. As Mr. Brown indicated, the primary thrust of this presentation is on sieve analysis. Many of you may be aware, and possibly not, that there are many types and techniques of sieve analysis. The throw action, the horizontal, the sonic, the wet, and the pneumatic, which we're going to emphasize on today. Throw action. Typically, this is the type of process where a stack of screens is mounted onto a mechanical apparatus, and the mechanical apparatus is either gyrated or hit with a hammer or an action causing for the particles to bounce within the cavity between the screens. As the material bounces between the cavity within the screens, the material then, those particles fine enough, will pass through from screen to screen to screen. Horizontal or oscillating. Again, a mechanical function is taking place where the material is shifted within the cavity of the screens. Again, here stacking screens. So the material then has to rely on the fact that the material is displaced from one level to the next, allowing the finer material to pass through the screens, through the entire stack of screens, that is. Sonic. Sonic is typically used for a finer type screen, a finer type material, and is utilizing a sound level which generates a wave of air, and this is typically performed at a higher frequency. Again, you're relying on the fact that the screens are stacked and the material must travel through the entire stack of screens. Wet sieving. Wet sieving is typically used when the material or suspension cannot be dried. Again, very fine powders. However, those fine powders have a tendency to agglomerate. Sieves are stacked. The sample is placed on the top sieve, and water is sprayed by means of a nozzle across the top sieve, which then transports the material from sieve to sieve to sieve. Ultimately, what takes place is the rinsing water is emitted clear from the bottom sieve, at which time the sieving process is concluded, and then the residual on the sieves must be dried and then weighed to determine the particle size distribution. Pneumatic aerodynamic sieving, our thrust today. Aerodynamic sieving utilizes the pneumatic sieving principle. The pneumatic sieving principle takes negative air pressure and draws the particles through a screen, creating a flow upward by means of a wand that rotates directly beneath the screen, as you see here where I'm pointing. The air travels, or the gas travels through the wand, distributes the material between the sieve cover and the cloth, allowing all the particles to become fluidized so that if there's blinding that may occur or larger particles block the path of a smaller particle, the particles then are moved around, allowing all the particles to come in contact with the screen, and thus the finer particles are carried in the gas stream onto either a collection device such as a cyclone or a vacuum. Typically here on this caption you can actually see a sample that is being distributed across the top of the screen, and as you see here, the volume of material is gradually diminishing while the screening process is taking place. Oops. Common applications. Applications are such that where quality control, an important factor, research and development, process monitoring, and as mentioned previously, small-scale classification, where clients want to have a separation of material for other factors or determination. Analysis immunities, particle shape, variable density, contamination, vibration, dust, and temperature. The operational parameters that ensure repeatability, and these are 4 key parameters. Sample size by weight, typically speaking, plus or minus 1 gram is the typical range. Sieving time, anywhere between 1 to 3 minutes, depending upon the initial starting size of the material and how fine you're analyzing. Vacuum pressure. Vacuum pressure nominally is between 8 to 16 inches. However, if the material is somewhat friable, then the vacuum pressure can be reduced down even finer, or lower that is. The most important, and again I cannot emphasize enough, is the cleanliness or the integrity of the sieve screen. This particular portion, or let's say apparatus of the sieving process is the most important, because without the integrity of the sieve screen being in place, the results that you will get from the analysis are questionable. So if the material on the sieve is wavy, is marked, is damaged whatsoever, at that point in time, the sieve then needs to be disposed of and replaced. Air sieving benefits. Well, as I mentioned before, the highly reproducible results, provided the operational parameters are held within a reasonable tolerance. Some powders have a high saturation of ultrafines and can stick to those screens from level to level on shakers or oscillating screens, blocking the passage of the finer material. With the airjet, this does not take place simply because of the pneumatic sieving the air that distributes the material across the top of the screen. Energy and time savings, 1 to 3 minutes per screen, whereas with the oscillating or shaking, approximately 10 to 20 minutes. Accurate results. The reason why the results are so accurate is because during the process, the fines are removed first. And as we all know, the finer the particle, the greater the surface area, the higher the potential of those fines becoming attached or agglomerated to larger particles, thus skewing the results. The rotating nozzle and the air that comes out of the nozzle as it's rotating dislodges or deblinds any of those larger particles that may have become blocked or blind the screen. Compact design, very small tabletop. Quiet operation. The noise level is comparable to that of a household vacuum. Cleaner operation. Typically during the operation of the analysis, there is no dust because it's operating under a negative operation, negative air pressure. This particular caption just gives you an idea of the effectiveness in time that air sieving has when compared with oscillating or shaking type sieves. As you can see here, within the first 30 seconds of operation, the air or pneumatic sieving device basically reaches its maximum or full effectiveness, whereas with the oscillating and shaking, it's substantially longer. All right. The air sieve device, the basic model, consists of basically the main unit or the main instrument and the vacuum. Operation, however, is relied on the operator. The operator must weigh and record the sample weights manually, and upon conclusion of the sieving process, the operator then must calculate the percent retained or percent passing. Whereas with the advanced model consists of, once again, the main instrument, the vacuum, the balance, the operational software, along with the required interconnection cables that allow for communication to take place between the main instrument and the balance and the computer which stores the software. The operation is quite simple. The operator enters the sample information in the beginning of the software process and then simply follows the instructions displayed by the software on the screen of the computer. The sample weights are recorded directly from the balance. The analysis results are then automatically displayed on the computer screen and can either be electronically saved or printed using the default printer attached to the computer. Upon completion of the analysis, the operator can vary the results by simply pressing a toggle switch to obtain either the percent passing or the percent retained. Additional benefits using the advanced model. As I mentioned earlier, the user-friendly software, which guides the operator through the analysis. The electronic recording of the sample weights automatically. Calculates the percentage passing or retain rather than manually having to calculate them. Creates linear, logarithmic, or Rosen-Ramler format graph. And while in the Rosen-Ramler format, you also have the luxury of being able to obtain 3 additional points, which are variable, anywhere between 0.1 to 99.99%. As I mentioned earlier, now you can save the data for future reference or printing. And as I mentioned here, the printing, you can now print in 6 different formats. That's 3 in percent passing, 3 in percent retained. This particular caption just gives an indication as to the arrangement or the style of the equipment that would be used in the advanced model setup. Your vacuum, your air sieve, your scale. Your air sieve and scale communicate directly to your PC, which of course is controlled by your keyboard and printer. For the basic model, it's strictly the vacuum and the air sieve. Notice the format or the environment as far as Windows, Microsoft Windows is either 2000 or XP. This particular caption gives a display here as to what one would see if utilizing the software. You see the Micron size, the sieving time, the weight of the empty sieve screen, the weight of the screen before sieving process takes place with the sample. Then the total weight afterward. Once I mentioned before about the parameters, you'll also have an indication here of what your vacuum pressure is. then the conclusion, you have your percent cumulative or your percent differential, which can be changed simply by pressing this particular toggle switch from pass to retain. Earlier in the program, I mentioned that the sieve screens are the most critical part of the entire analysis process. The air sieve utilizes a wire cloth sieve screen in micron sizes from 20 to 4,750, otherwise known as 635 mesh to 4 mesh. However, in the 63 millimeter diameter size, which is displayed here, you can also obtain screens down to 5 micron. These are typically nickel etched screens, and of late we've been able to obtain 10 and 15 micron nickel etched screens in the full size. The screen specifications. Each screen is supplied serial numbered and accompanied with a certificate of conformance. This is vital when it comes time for assurance and complete traceability. Each screen is constructed in 304 stainless steel frame and utilizes 316 stainless steel cloth. The screens can be autoclaved to eliminate any contamination of bacteria from sample to sample. Each test screen is supplied with a larger standard 200 millimeter with a new gasket. Each screen is shrink wrapped and individually boxed, barcoded for quick and easy identification, but also insurance that the screen has not been previously used. And lastly, there are no crevices, rivet holes, or epoxy in the product area that would enable any of the material from being electrostatically attached, causing for skewed results. Lastly, the system can be mated with a downstream cyclone for those cases when clients wish to have additional separation or classification of the sample. This allows for further evaluation of the collected sample, and it also can act as a, as I mentioned, classifier.
Now we begin our question and answer forum. As we are limited on time, we will try to accommodate all the questions, but apologize in advance if we are not able to answer all of them. If we are not able to answer your question at this time, someone from Hosokawa will respond to you offline at a later date. Okay, Tim, the first question I see here. Is it possible to use more than one sieve screen at a time?
This is a question that's asked by many people when considering the pneumatic sieving process of an airjet sieve. The answer to the question is no, and it is primarily due to the fact that if sieve screens are stacked, what results is the fact that you cannot distribute the particles on the uppermost screens as effectively, and quite frankly what's occurring then is you're encountering the same problem that could take place if you were stacking the screens on an oscillating or shaking device. I must admit, however, as it was displayed in the captions, there is an adapter that can be utilized with the 63 millimeter screens that will allow 3 different sieve screens to be used at one time and of 3 different sizes. So the direct answer to the question is no, you cannot stack the screens, and one screen at a time is commonplace. However, if the samples are small enough and the analysis is requiring multiple, you can utilize the small sieve screen adapter.
The next question, what does the 8 to 16 inches of water mean?
Typically speaking, this is the amount of vacuum pressure that you would be impressing upon the particles. So the velocity of the air and the vacuum that's being pulled through the system is measured in inches of water. The inches of water are such that the vacuum, you do not want the vacuum to pull any greater than 16 inches of water column during the operation. If you go higher than that, there is a higher potential that you could degrade the material, thus skewing the results.
Next question. Can the results be compared directly with a shaking or oscillating sieving device?
Well, quite frankly, not to be, blunt here, but the answer to the question is no. And the reason why I say that, and the true reason is that the pneumatic sieving principle removes the fines first from the sample. Whereas with the stacking of the shaking or oscillating style, the sample is just basically entered, it is deposited on the uppermost screen, and all the material must pass through the stack of sieve screens. Again, that the higher potential that the screens can be blind, not permitting those finer particles to pass through. So in many cases, you will find that your results will definitely be different.
The next question. What is the minimum particle size the jet sieve can separate?
Typically speaking, depending upon the screen that's used, the nominal size range is between 20 to 4,750. That's in the wire woven cloth screens. When you're dealing with finer particles, however, the sample must be much smaller, you can remove 5 micron and below. So to answer that question effectively, you can pretty much go from 5 micron to 4,750. However, the nominal size range is 20 to the 4,750.
Next question. I have a row tap. If I were to replace this device with a pneumatic sieving unit, what effects would that have on my particle size analysis?
Well, quite frankly, you may find that you've been overgrinding your material for quite some time. The reason and rationale, once again, goes back to the fact that when you're using a row tap, which is a stacking apparatus, relies on the shaking and the bouncing of the material within the screens, you could potentially, and it does occur, you blind the screens. So when you're using the air sieve allows all of the particles to come in contact by removing those fines first and gradually working your way up to the coarse material. So as I mentioned initially, you will find that the results that you get from an air sieve will be, potentially finer than that from an oscillating or shaking, which could directly relate back to lost revenue and a higher expense to produce your product. The product, because now you have to overgrind the material to be able to meet the specifications that is required.
The next question. Can we use larger sample weights? For example, 100 grams. We are looking for impurities that are much larger than our product and represent a very small fraction of the total weight. We are currently using 20 and 40 mesh dry screening.
Okay, the area between the sieve cover and the cloth is somewhat limited. However, we have been able to extend that area, allowing for more sample to take place. You're dealing with a coarse wire cloth there, so it's not going to have the greater potential of blinding because of the volume. Some clients have used as little as 5 grams of material, and then I've had clients use as much as 100 to 150 grams of material. Keep in mind, however, we're talking gram weight. Gram weight is going to be based upon the density of the specific sample. So don't take my statement as saying 100 to 150 grams as law, because I don't know what the density of your material is. But yes, you can use a higher volume of material.
Next question. I'll read it verbatim. Typical repeatability of sample between several lab technicians. Sample placement on sieve effect results.
In some cases, sample placement can affect the results. However, let's keep in mind, what's occurring here is we're removing the fines first. What'll occur is, if someone places a sample in the center of the screen, it's going to rely on the rotation and the velocity of the air to distribute the material to the exterior. More cases than not, it's not going to have an effect if material falls through into the bottom cavity, because once the vacuum is started, it's carried away by the gas stream or the vacuum stream. Now, as far as from technician to technician, it is important to stay approximately 1 to 2 grams plus or minus in the volume of material. This way, you can maintain your repeatability. In addition, you also have to try to make sure that your vacuum pressure is staying the same. All right. So I would say in answer to that question that there would be very, very minimal amount of deviation from technician to technician utilizing a pneumatic sieving device.
The next question is, what is the meaning of D10 and D95?
D10 and D95. It's basically the diameter at the 10 percentile of your total analysis. D95 is the diameter of the micron at 95%.
Next question, is there a way to verify a sieve to show that it is damaged or not damaged?
Well, in many cases, just observation of the sieve can be performed. If you can visually see that the sieve screen has a deformation, or if it's wavy, that is one method. Some people actually just take the sieve screen and look at it through, or hold it up and look at it through a fluorescent light. Yes. But from the standpoint of damage, in many cases, you may have to have the sieve recertified if it's not visible. So, you know, more cases than not, you're looking at the visual integrity of the screen. And the best way I can define the visual integrity of the screen is, as we're all familiar with, air conditioning units, the condensers. If you recall, the coils of the condensers are fins. And if you deform those fins, what will take place is you'll lose cooling efficiency. So if you deform the openings of your sieve screen, you're going to lose the integrity of the analysis.
Next question, the number of screening attempts in between cleaning of sieves.
That's going to be dependent upon, number one, your product. It's going to be dependent upon, number two, the size of the opening. There is a recommended frequency of cleaning. Keep in mind, the smaller the opening or the smaller the aperture, the more frequent the usage. So, for example, a 45 micron might be cleaned every 6 months or after every 30 operations. It's really going to be dependent upon the individual application and the material that's being analyzed.
Okay, we have time for one more question. If we were not able to answer your question, again, as I mentioned prior, we will address your questions offline at a later date. The final question, how do I get an indication of particle size distribution?
Typically, when using the automatic method or the advanced method, you will get a particle size distribution plot as a graph format. Otherwise, what you would then do is just plot out based upon your micron size and the volume of material. You can get a relative point-to-point indication of your particle size distribution.
Thank you, Tim.
Thank you.
We at Hosokawa Micron Powder Systems sincerely thank you for your time and attention today. Please refer to our website, hmicronpowder.com, to view upcoming educational webinars. If you have any further questions or requests, you may contact Tim Calvo directly. His contact information is displayed here. One other note, this presentation will be posted on our website. So, if you know of any colleagues who may be interested in viewing this or prior webinars, they may do so by accessing our website. Again, we thank you and good day.